So yes, structural refinement types is a joint work with Ingo, Skupin, Lawen, and Klaus Ostermann, who are all here at ICFP. So please feel free to also talk to them about this topic. So let's jump right in. Consider the following predecessor function on piano natural numbers. This predecessor function has no case for 0. And the question is, what type should we give to that function? So the obvious case is natural numbers to natural numbers, but this is of course not sound, because if we apply the predecessor function to 0, the program gets stuck. So what alternative do we have? If we work within a system which has polymorphic variants, say OCaml, then we could consider the successor constructor to be a polymorphic variant. In that case, we would infer the following type for all A, and then we have this polymorphic variant which contains one constructor. As A, we return the alpha. But this is also not what we want. This is too permissive. So in a system with polymorphic variants, we would allow to apply the predecessor function to the successor of true. It's perfectly sound. It returns true, but it's too permissive. We don't want to apply the successor constructor to true. We want the type system to reject that program. So those, if we combine the two systems, we get something like this, which we call structural refinement types. So on the left-hand side, we have registered that we do require a non-zero natural number, and the n with the top, which we call the full refinement type of natural numbers, means this can be any number. So we take a non-zero natural number and we return any natural number. We can, this is the full refinement is just an abbreviation. So we use equi-recursive types written with the small mu. And this is just like a structural encoding of piano natural numbers. In the following slides, I will inline this definition. Yes. So the basic idea of our paper is if we combine the typing rules for nominal data types and combine them with the rules for polymorphic variants, we get this new type system, which we call structural refinement types. So the nominal part, you can see here. So the yellow part in the resulting type comes from the nominal parts of the typing rules, and the red part that I've marked here, they come from the typing rules that we inherit from polymorphic variants. In the whole system, no type annotations are required, and it includes subtyping, so this can potentially be a very difficult problem, but we didn't have to do any of the hard work. So we built upon other people's previous work. So any refinement type system requires some notion of subtyping. Any function which accepts natural numbers should also accept non-zero natural numbers. But it has been well known that like the combination of subtyping polymorphism, parametric polymorphism, and the complete inference of printable types without requiring the user to annotate anything is a hard problem. But we built upon the work on algebraic subtyping by Stephen Dolan, who's also in the audience and gave a talk, Dolan and Mycroft, and also the presentation of Lionel Perrault at ICFP 2 years ago. So they basically show how to do a type inference in a system with parametric polymorphism and subtyping. The basic idea, I can't go into the details, that is similar to a Hindley-Milner type inference, but instead of type equality constraints, whereas type sigma equals a type tau, we generate type inequality constraints. Sigma is a subtype of tau. There's a constraint solving algorithm for those subtyping constraints, and associated machinery. So let's look at some of the rules and how the typing rules are combined. At the top left, so here we consider the typing rules for just the successor constructor. On the top left, you have the typing rule in a nominal system. On the top, on the top right, we have the typing rules in a system for polymorphic variants, and at the bottom, we have the combined rules. So from the nominal system, the characteristic property is that we require the argument to the successor to also be a natural number. And in our combined rule, we express this by requiring that the argument to the successor is a subtype of the full refinement of the natural numbers, which is a constraint which is generated during constraint generation. The characteristic property of the typing rules for polymorphic variants for a constructor is that the type that is inferred for a constructor reflects the constructor that was used to construct the term. And in our combined rule, you can also see that the constructor that was used to construct the variant is reflected in the type inferred for the constructor. Similarly, for pattern matches, we combine the typing rules that you would have in a normal system, and we combine them with the rules that you would have in a system for polymorphic variants. I won't go into all the details, but just show the characteristic properties. So in a nominal system, if you pattern match on the successor constructor, you know that the x that you bind will be a natural number. And in the combined rule, so in the last premise in the combined rule, we get an x of type tau into context, and we generate two constraints, which are written like the above in the first premise, that the type tau must be somewhere between the empty refinement and the full refinement of natural numbers. The characteristic property of pattern matches in polymorphic variants is that on the destruct T of the pattern match, we only require it to contain those constructors that we actually pattern match on. So if we don't pattern match on, so here we only pattern match on the successor constructor, and so we only require the successor constructor to be present in the type of the destruct T. And this is also the case in the combined rule, where we have the destruct DE, and we require it to be to contain the successor constructor. So this was this is our entire basic idea. We combine those two rules. We build upon the algebraic subtyping system. We don't require any type annotations, and we infer those refinement types. So what will you actually find in the paper? The big question is what do you have to do for parameterized types, like lists of elements of A? So consider the following term. It's a two-element list. The first element is a Boolean. The second element is a string. And there are, in principle, two different types that you could, two different refinement types that you could infer. The first alternative is this one. You infer a two-element list, where the first element is a Boolean and the second element is a string. The second alternative is this one, where you infer a separate refinement for the spine of the list and for the elements of the list. So you should read this type as it's a two-element list, and the elements are either Booleans or strings. So this type is certainly more precise. It contains more information, but maybe it contains too much information. And as I said, all the types are inferred, so you have to decipher all the types that the system infers for you. The second one is less precise, so we don't know which element is at which position in the list. But it's maybe more modular and easier to reason about those separate refinements. But what this requires you to do is to have some kind of refinement types at higher kinds. So here, this is notation for the refinement of a two-element list applied to the type Boolean or strings. And the whole complexity is how do you do algebraic subtyping at higher kinds. And so in the paper, you will find all the technical details. I won't go over them. So there's constraint generation rules. How do we generate constraints for arbitrary user-defined types? How do you solve those constraints? You also have to simplify them, so we encode them in automata and use automata simplification to simplify those types. And there's subtyping rules, but yes, there's no time. So what are the main takeaways? It's actually very simple to implement. assuming that you already use this algebraic subtyping system. If you use another type inference system or don't bother, it's probably not going to adapt easily. But if you're in the system, those kind of refinement types are very simple to implement, and there's very little additional code. You just have to generate some different constraints within the given system. They're expressive enough for many interesting use cases. So one of the examples that we have in mind is you have an AST type, and then you have a desugaring phase which removes AST nodes. So you want to express the property that after the desugaring, some AST nodes are not contained anymore, and you have to remove them recursively. And this is perfectly expressive enough to infer this type and yes, to use it this way. And it does not require anything but familiar type inference machinery. So there's nothing involved like in other refinement type systems like SMT solvers or like that. It's ordinary type, well, not completely ordinary. It's using subtyping type inference, but it's just type inference machinery. What remains to be done? What haven't we managed to do in the paper so far? The future work is to develop the formal meta theory more formally. So the type soundness properties, we think that we can just adapt the existing proofs of Lawen and Perot. And we are also currently working on doing this formally in Coq. We want to investigate the formal expressivity properties. So the types that you can express, the expressivity of the types is that you can express regular sublanguages of types. So for the example of piano natural numbers, we are able to express piano natural numbers which are even, but we are not able to express piano natural numbers which are primed, because prime is not a regular predicate. And also the kind of types that are inferred do correspond to a very simple control flow analysis. So it's like a 0 CFA, but we want to make this connection more formal. The types that are inferred very closely follow the syntactic structure that you have used in constructing your program. So in a desugarer, for example, you in each output path, you do not produce the AST nodes that you desugar, so they do not appear in the output types. We want to do larger case studies, especially in order to study the complexity and whether the scales. And the biggest pain point at the moment is usability engineering. All the types are inferred, and they can be very precise and very verbose. So we have to find some ways to kind of shrink the inferred types and make them more readable. At the moment, sometimes you can convince yourself that the type is correct, but it has reflected too much information, more than you actually wanted to have. So that was my presentation. I have no idea how much time I have used. Maybe I was too fast. But yes, I'm happy to take any of your questions. Thank you.